So, we're on chapter 2 now, and this is one of those classes, like biochemistry, that you really don't want to get behind because it just keeps coming. And there is a fair number of the chapters that will build off of each other simply because the original chapters are like calculation methods, right? And how to use tools. And then the later chapters will build off you actually using those tools. In real world situations. And you will see the actual real world situations. They are literally studies and they have references. So this is not fake real world where we make shit up. Oh, look at that. I was thinking whether I'd have to do something evil. Okay, so honestly, the first parts of these, it's kind of funny that I do this like PowerPoint, right? And I put these first 3 things in there, and the first 2 are each one page, and they are probably the most important things I could say to you, period, like will save your life and career, okay? So safety is a game of preparation. If you walk in and you don't know what a chemical is going to do to you, then you really need to make extraordinary safety measures. Like it doesn't even come in contact with the air, okay? It has no ability to come in contact with you at all. I did that a lot. I used to work with a lot of stuff that the only thing we knew about it, it's kind of has the same functional groups and arrangement as a nerve gas agent. So we don't know what it would do to us. One whiff might kill us all, okay? Yeah. And I worked with a few things that I knew for a fact would just explode on contact with air. Any level of oxygen over like a molecule per centimeter is going to blow it up. So I have to be incredibly careful, right? It's a whole different level of safety. However, most times you can actually limit your exposure by simply knowing what you're working with. Now, why do I always harp on this? When I was a graduate student just starting out, 2 top-tier graduate students, really elite, had a great future ahead of them, died. A horrible, painful death over 2 weeks where their immune system literally destroyed itself. And they did this because they were doing a simple cracking. You guys remember organic too. I do that. I crack a compound for you. They were doing the same thing. They were getting this 4-membered ring, which is what I work with a lot when I was a graduate student. And it actually, it broke. It spilled. They didn't know what they were making. They didn't look that up. And so they put on 4 layers of gloves, and then mopped it up with paper towels. And it absorbed through the gloves into their system. It happened to be something that would bind to their immunosystem, and it destroyed and killed off their immune system. And then they died horrible, painful deaths over weeks. It was really nasty, really something you should feel sorry for, but a big warning, right? I mean, these are not stupid people, right? They were some of the best chemists in the world. At least best trainee chemists, I guess. And yeah, it used to be when I was coming up through the ranks, they still had people that were in the days of what's called picric acid. And it was a pretty common reactant. And picric acid, which by the way, we used to have like a 1-liter container before we moved buildings. When it dries out, it explodes with any sort of violent shaking. Like if you bump it, it'll go boom, okay? And people used to be at these conferences and they wouldn't have fingers. They'd be missing fingers and sometimes entire hands. Yeah. And I used to know a guy that would take his claw and he'd grab stuff and then dip it in liquid nitrogen with the claw. So we had like really good warnings. We've gotten good enough now that you don't get those warnings in your generation of the previous generation having, fucked up so much. Like, look at me. I just have a little scarring in my retinal tissue. You can't even see it most days. I've done pretty good. All right. Watch me get like some horrible disease 10 years from now. This is what I get for bragging. All right. Again, you need to make sure you have adequate safety precautions. You need to make sure they actually work. I actually fucked this up a year ago. I had a reaction under a fume hood, and I flipped the fume hood on, and I didn't actually test and see if it was working. I just started doing it. And the fume hood was not actually vacuuming. It was just making a sound, which when I, realized it later on, I realized it wasn't the full vacuum sound. It was just like a motor turning. So I got tricked out, and I breathed a bunch of chemical that I really shouldn't have. Okay? So it happens. However, I could have died from that, right? And God knows what that's going to do to me in like 10 years, right? Yeah. So be careful. Know what you're working with. Understand exactly what that's going to do with you when you screw up, okay? Have in place safety measures. How many safety measure layers should you have in place? Should it be, I won't let it be near fire, so it'll never burst into fire? Is that good enough? No. How about if I have an extinguisher? Is that good enough? No. I need multiple safety layers. The rule tends to be 5 layers, okay? What does layers mean? It means that if this doesn't work, I can do this. If this doesn't work, I can do this. If this doesn't work, I can do this. And you should be able to fall back at least 5 times. This is for regular lab safety work. I laugh every time I see things like the Shenzhen lab, where the COVID may have originated, that they deleted the data, so we'll never know. Yeah. Good. Well, we'll talk about that one next. They didn't even have lab procedures in place that would have been safety-wise acceptable for a normal chemistry lab. Forget one engineering deadly viruses. What the hell were these people thinking? Like every time I hear anything about their safety procedures, they weren't even close to up to standard. Not even near it. Jesus. It should not be, hopefully it won't fail. It should be, it cannot fail. There is a 1 in a million chance, and even that is split into 10. So your lab notebook is probably the single most important thing you'll do. Now, let me preface this with a little bit of history lesson, because I think it's actually very important to understand where people were before science, okay? So China has 6,000 years of scientific literature. Do you know that? Yes. China has alchemy documents and books about different medicines and reactions that are more than 6,000 years old. And so they have documented history reaching 6,000 years of history. An unbroken chain, okay? They're the only country in the world that has that. They're the only society in the world that has that. Now, so China had 6,000 years of development in medicines, chemistry, physics, everything you can think of. Why did they not get up to steam engines and everything else? Did you know steam engine was developed 3 times through history? It was invented 3 times that never led to anything. It was only the 4th time that we know of that was invented that actually led to something. Why is this? Well, China's big reason is because there's literally a saying in Chinese that to let a genius survive and to let their legacy survive is to harm yourself. So literally a folk saying that says kill off anybody smart enough to invent stuff and then burn their records. Okay? So why didn't they ever amount to much? They kept burning the damn notebooks, right? What's the most important thing that came about due to the scientific revolution? the last part of the scientific method. Share. Document, share. Document, share. And so what it lets happen is a superhuman effort. One person can only do so much, right? They can only come up with so many ideas. They can only test so many ideas. They die. They don't keep records. It's over, right? Everything has to be restarted, and so we never get anywhere. However, with good lab notebook documentation, you're going to put everything that somebody would need to see why you did something, how you did it, and then what the results were. And not what you think the results were. You need to put in actual scientific truth, right? What was done, what was observed, and it needs to be understandable to others so they can draw their own conclusions from it, right? There is going to be bias in this. It helps when you practice. You can reduce that level of bias by letting other people actually see it afterwards, okay? Now, full disclosure, you probably do want to keep your notebooks secured and not accessible while you're working on something before you publish, okay? There's a lot of cases of people stealing results from other people, right? And it's been really bad over the last few years. So,
do you mean that as far as stealing it to consider as their own work?
Yeah. Yeah, stealing your results and publishing them as their own. There's been hundreds of papers retracted because of this.
I remember you mentioning that like a bunch of papers are doing that, and then oftentimes what they have down for their information is not true.
Yep. There's been falsifying information, which is one thing, okay? And good laboratory notes will keep you from getting in trouble for that. But on the other hand, there's also, eventually you want to share these lab notebooks and everything, right? But you want to do it after you publish or with somebody you deeply trust. Because I know of at least half a dozen people I just know, period, that have stolen research from another person and published it as their own. And they beat them to the publication. Now, to be honest, if you keep really good lab notes, you're going to be able to sue them and get recognition or the results of that. For example, Charlie Towns, who was the inventor of the laser, he's the one that actually invented the method of making a laser. He got no money at all from that. His graduate student, however, is a multimillionaire and retired because the graduate student came up with the name laser and had lab notebook documentation of him coming up with that acronym. Okay? So good notes really make a difference in life. Probably the most important thing about the entire scientific method. Okay? All right. Remember that your notes, though, have to be able to communicate to other people, and they need to try to reduce the bias as much as possible, okay? You're not giving final conclusions, right? It needs to be how you did something, why you did it, and what the actual physical results that you could detect are. And try to give us everything that you can detect. There's a very famous scientist from Johns Hopkins who got the Nobel Prize. He got the Nobel Prize, but he actually took much longer than he should have. So Raman spectroscopy was invented later on, like further down in his career, about midway through his career. He had been taking all these spectra, and he thought these were artifacts that he was seeing, and he was actually recording Raman spectroscopy before anybody ever knew what it was. But he did such a good job keeping notes that he could then go, and the reason he got the Nobel Prize is he had hundreds of Raman spectra that he just published, bam, 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 hundreds of papers within a few years because he kept everything. Smart, right? Good thing he had good notes, even though he couldn't figure it out himself. Somebody finally did, but he was there, right? Which is its own genius, right? This is the electronic balance. It's a thing that you've used so much that you think you know how to use it, but you don't. Okay? It's deceptively simple. And so this is how electronic balance works. Honestly, you're better off looking at your diagrams in your book and just following through, okay? Essentially, there's a lever that's going to measure your mass times gravity, otherwise known as weight, right? And so it is actually the correct terminology to say I am weighing something, because you literally are weighing something on Earth. You can't do anything but weigh stuff on Earth. In space, you could theoretically do a mass calculation based on gravity if you're far enough away from a gravity well, but that's not trivial. It's a lot of money and effort. So we're not doing that here. By the way, if you used a balance up on Mars or the moon, it would not work properly. You'd have to recalibrate. Okay. So anyways, what it's going to do is essentially going to move a lever. The circuitry inside is going to counter that force, so it's not moving anymore. And that's going to give you a certain amount of electricity that's using, which will give you a reading on it that is your mass. Okay? Keep in mind, anything that throws off how that pan transfers force through it is going to mess up your measurements, isn't it? Okay. So, lots of things that can mess up your measurements. This is one of the things that you kind of know how to measure on a balance right now. You put something room temperature on it, right? That you're going to collect in, typically. And you tear that off. You carefully put your bottle so its mouth is above what you're measuring into, and you carefully move small quantities that you can easily control, right? Why was I so stressed on not allowing anything to ever spill? Yeah, you spill, it's going to spill in the balance. You're going to think you got the right measurement, but you don't, right? You'll screw your measurements up. Does anybody know what hygroscopic is? It means water absorbing. So, did you guys ever measure out any like NaOH? I know you guys measured out a number of hygroscopic compounds when you're in organic chemistry. You'll remember me saying, don't leave the damn bottle open and yelling at people, and that you need to measure it quickly. Okay, good. So this is a method to weigh by difference that's much better method than you normally would use. So what you do here is, instead of tearing off your beaker or whatever you brought to put it in, you tear the bottle, okay, with the lid on. And then what you do is you have everything set out right next to it, so you can then open the bottle, transfer, roughly what you think you need, close it up again, and then you put the bottle back on the balance and you measure that difference. Okay? And what that does for you is that the beaker with your stuff in it is going to continuously draw in moisture. And if you look closely, some of those hygroscopic bottles actually started developing beads of moisture in them, right? Because in those levels of labs, I have people leave them open all the time. And you would have noticed your beaker actually started developing like a solution after a while, right? And if you go in our rooms, the inorganic one, the Gen Chem one, if you go in that chemical room that stores all the chemicals, you'll actually notice that some of those bottles are dissolved. They sound like they have solid in them. If you read the label, they did have solid. But somebody stole the the dehumidifier from the damn room. For a long time there, when I wasn't managing things, it did not have a dehumidifier, and those bottles are now dissolved. Okay. Did you understand how to weigh by difference? It's actually an incredibly useful method. And you can pretty much do that with anything, by the way. In some ways, it's actually a better method than weighing into something, right? Because you can put it directly into the container you're using. Like if you're using a micro kit. Okay, you will notice that most of our balances are not set up right because we just don't have any space or option to do it right. You need to locate it on a heavy table. Typically, you want to use a marble slab. You'll notice the only balance that's done right is the analytical balance that's in the middle lab. Remember where the spectrometer is? There's a balance on the right. That's the only one done right. And it's only partially done right because they put the damn air conditioner in there. It's the only space we can do it that people won't bump and mess with it all the time. So, anyways, you'll notice the tables in the two labs are not the proper types of tables. They don't have heavy marble slabs, and so they're actually quite light and they vibrate, right? Yeah, all the time. And you may have noticed your numbers vibrating all the time on the second to last digit. You're losing quite a bit of accuracy, right? You need to keep the object to be weighed close to the center of the pan. I see this done wrong all the time. Why are you doing it close to the center of the pan? Because there's a lever in there, right? If you put it to the sides, it increases the lever force, doesn't it? And so you're transferring the force incorrectly. It needs to be ambient temperature. What happens if it's not ambient temperature? There is physical matter all around us, right? So what happens if you heat up that physical matter around us, air? It lifts stuff, right? If you cool it, it sucks it down, doesn't it? And so if you change the temperature under that pan or the pan itself and the lever going in, it will actually change the weight of it, because it will either float or it will sink. Because we exist in a solution, essentially, right? Weird, huh? Need to place the sample in a desiccator during cooling to prevent accumulation of moisture for anything that has any degree of ability to absorb moisture in it, okay? Do you guys remember desiccators? There's those glass bowls with the lids, right? And the powder on the bottom. Those are desiccators. Always check your desiccator to see if it's the right color. The desiccant has color change that happens as it gains moisture. Okay? You can actually look it up on Google if you forget. Which I'm not embarrassed to say, I have forgotten a few times because I just get so damn tired because there's too much stuff going on. All right, so you always close the glass doors, prevent drafts from affecting the reading. You will notice the analytical balance, the last two digits will move constantly from your breathing, even if you're just in the area and not breathing directly on it. You need to close those doors, especially with air conditioning and stuff. That really gives a problem. Fingerprints can affect the apparent mass of an object. Typically, you want to use some sort of tweezers or tissue or scupulas or gloves or something, right? Because remember, you are existing in an aura of your dead cells and various different debris coming off of you within 3 feet of you. So you contaminate everything all the time. Anything you touch is getting covered in the oils that cover you, right? Which, by the way, you need. Without those oils, you would have a lot of problems, okay? Your skin would start dying. But you're covering everything you touch with them, right? Okay. By the way, did you know you're an ecosystem? You have an ecosystem of symbionts that live with and on you. Yeah. There's even new ones that are evolving right now. There's a type of skin mite that is evolving to clear our pores right now. Cool, huh? Buoyancy corrections. Remember, we exist in a solution, right? And so it's like something in water. You know, even if something doesn't technically float, it doesn't mean it doesn't, it sinks as fast as it would otherwise, right? And you've seen that a lot. When you like lose something and it starts sinking, a lot of stuff doesn't go as fast as it would through like air, right? And that's because it has some degree of buoyancy, okay? The closer to the density of air, the greater the buoyancy. And this is the formula right here. That's essentially what it tells you, is the closer it is to the density of air, which is right here, at these conditions. Remember, the density of air is going to change depending on the pressure and temperature. This is the density of the calibration weights, not the water. Okay. This is typically a constant for a machine, all right? And they typically use a constant value for pretty much every machine, okay? And then this is the density of the object being weighed down here. And essentially what this is doing is giving you a correction that would change your mass you've weighed by a factor that is how buoyant it is in the air. Okay? Notice if you did something like a helium balloon, it would be really buoyant, right? And this would shoot way up. If you were to graph these, you'll see a curve like this. Notice the higher the density, the closer it becomes to not being buoyant at all, right? See that? Okay. However, there is an inflection point. You'll see right about here. And this is because once you get a certain degree of buoyancy, it's no longer as, it's less buoyant than the weight, the standard weight. You see what I'm saying there? So the standard weight has some buoyancy. What we're measuring against has some buoyancy. At this point, you about match up to it. Okay? But again, even if you go way over here, this does not shoot up as fast, okay? This is a pretty gradual shoot up, so you'll still stay pretty much very, very little buoyancy, okay? And then know what would happen if you did this on somewhere like Venus or Jupiter? Both of those have way higher density. And so your stuff would be way more buoyant, right? You could have like steel ball bearings and they'd be buoyant on Jupiter. Okay. All right, so measuring volumes. Volumetric flasks are used to prepare solutions with a known volume. Transfer pipette is to deliver fixed volumes. Those are the ones that have the bulbs in the middle. You use a bulb at the end, and it has just one line, right? And you transfer 5 milliliters, 10 milliliters, 25. You get the idea, right? Volumetric flasks are those flasks that just have the single line, right? These are actually the most accurate ones, okay? I know it probably doesn't feel like that to you, but they are. Those are your most accurate ways of measuring volumes. The larger your glassware, the smaller its relative uncertainty, but the larger its absolute uncertainty. What does that mean? If I'm weighing out 1,000,000 liters of something, and I'm 1 liter off, I have very small percent difference, right? I'm way less than 1%, right? That's great. But I'm still 1 liter off, aren't I? So my absolute is large compared to like, a pipette that doesn't even hold a liter, right? But if I were to be using a pipette, I might be 10%, 20%, 30% off, right? Because any error I have is a large percentage of it. Does that make sense? Okay, you absolutely need to understand the accuracy of your glassware before going in. It's very easy to select the wrong equipment, okay? To select something that is not the accuracy you think it's going to be. You need to understand how to design a serial dilution to make a less concentrated solution from a more concentrated solution. You need to do it typically by transfer pipettes and volumetric flasks. The reason you want to do this with transfer pipettes and volumetric flasks is when you do a serial dilution, your errors are going to stack up, right? If you do 10 measurements and each of them has a 10% error, you're going to have a lot of error at the end, aren't you? Okay? But if you do 3 dilutions and they only have a 5% error, you've really reduced your error, haven't you? So how you design your dilution and the equipment you use can make drastic differences. I mean, really, truly drastic differences. You could be 30% off in one case and 1% off in the other, okay? And bad design really screws up a lot of things. Like Intel had a terrible run of it because of bad accuracy designs by the people that were supplying them their gases for the printing, the circuit design process. making their different chips. They had too many impurities in them because of bad measurement practices. And it costed them billions of dollars a couple of years ago. I mean, really, really messed up their entire financial. They had a bad time. The president of the company actually had to step down and they got a new one because they kept missing deadlines. Yeah, it's bad. Anyways, gives you an example of a real world. You can really screw things up by bad measurements. All right. This is burette. It has a stopcock right here that you open and close when you're doing this. Burettes are fairly accurate measuring devices. You always need to try to measure in between the lines. Remember, you should be able to measure fifths in between the lines. Okay? There's a difference between it being on the line and it being halfway, right? And you can tell that. This is how you perform an operation with a burette. Do you have any questions on this? Okay. Make sure you actually read this and don't just assume you know. Okay? It's very likely the only time you've done this, general chemistry, that you didn't do it right. All right? And it's very likely you did it wrong. And not only did you do it wrong, but you don't remember it that well anyways. So, you not only did you forget, but you did it wrong in the first place. Okay. Pretty much everybody does it wrong the first time. That's okay. That's why we have this class. Relative uncertainties. So relative uncertainty is going to be uncertainty in a quantity divided by the magnitude of the quantity. Think of it as relative as percentages, right? Relative to something. Absolute would be just the number, right? Each are useful in their own way, okay? So absolute uncertainty can be useful, but is oftentimes used to mislead. You guys ever heard of that or seen examples of it? Okay. What if I tell you, oh shoot, the only example that came to my mind is absolutely going to get me in trouble if I actually talk about it. Damn. I mean, what if I told you like 1 in 100 people gets arrested for something? Is that a lot, or not a 1 in 100? 100 people a year get arrested for something. Is that a lot or a little?
Well, is it in like one place?
Exactly. Exactly. It's not relative to anything, right? You have no reference to compare. Is 100 people a lot or a little? I mean, for like Mackenzie, that's a lot. Bethel, that's a lot. New York City, that's nothing, right? That's the murder rate like Friday. Like that's just not a meaningful number for that. And so when you hear things like, you heard it for COVID, right? The vaccine, the J&J vaccine, 1,000 people had this heart condition thing, but that doesn't really tell you all the entire information, right? Because how many people actually took the vaccine? Well, 1 billion. Is 1,000 out of 1 billion a lot? No, that's actually pretty small, isn't it? A lot less people than got COVID and died. Okay? Now, on the other hand, I would not probably take that vaccine for the new variants of COVID. That probably would be a bad idea. Which some governments are actually requiring people to take. Wow. But anyways, that's a whole other thing. So you can use larger volumes to make up for to get a better relative uncertainty. Because typically your uncertainties will be absolute uncertainties. And there's a lot of them that are just because you're a human, you can only do certain things, right? Those typically are absolute uncertainties. If you increase your volume, you can typically lower those relative uncertainties and just take the sample amount you need out of it, okay? However, this gets to be very wasteful, and it also, at a certain volume, it just becomes unmanageable, right? Unless you have specialized equipment. So a certain burette has an uncertainty of plus or minus 0.05 milliliters. You know this is an absolute uncertainty, right? Because that's an amount. What time is it, by the way? Oh, wow. Whatever that was got out early. So if you deliver 20 milliliters and then 40 milliliters each, notice your relative uncertainties are very different, aren't they? Because again, your absolute uncertainty is because of things like you're only so fast at closing that stopcock, right? And you can only read certain amounts between the lines, can't you? Your vision just isn't that good. And so when you deliver different volume amounts, you get different relative uncertainties. 20 milliliters gives you a relative uncertainty of 0.25%, right? 40 milliliters would give you 0.12. You see how you doubled your relative uncertainty by delivering less. Kind of interesting, right?
So how does the uncertainty relate to percent error? Like if the uncertainty, same like in larger volumes, you have a less of an uncertainty, it decreases.
Relative uncertainty decreases.
Yeah. So how does that relate to like if you have a smaller volume, obviously your relative uncertainty is higher.
Your relative uncertainty actually will increase in an exponential function as your volume goes down. And there's a point where, this actually becomes intuitive to a point. Like if you were to try to deliver exactly one drop with a burette, your relative uncertainty would skyrocket into, damn near infinity, right? You'd be almost certain to get it 2-3 times wrong, right? Like if you did it 10 times, you probably got it wrong 10 times. Maybe you got it right once. Maybe. Now, percent error is a related but slightly different concept. And remember that these aren't actually errors per se, they're uncertainty. Okay? You don't know if you got it right or not. And you'll never know, probably. You would have to remeasure it completely. In which case you can't do whatever you're trying to do, right? So you'd end up in a closed loop of doing, measuring, which they do actually. That's how they come up with these uncertainties, right? That's how they come up with these absolute uncertainties. And they put them on the glassware. They literally do that. They do measure against something, they do that a few times. Enough time to get some reasonable confidence in that uncertainty. Now, a lot of people do call this error, but that it really isn't, it isn't actually error, okay? Yeah, it's what you don't know. You could be perfect, like somebody can throw a dart and not even look, and sometimes they hit the target, right? But you don't know until you actually check, right? And that's kind of what we're doing. We're throwing darts, and we're using something to try to help guide us, but sometimes we hit the target exact, sometimes we're a bit off, right? And we'll never know. And we'll talk more about that type of error and that type of error versus uncertainty and types of uncertainty and errors. And there's actually a lot of depth to this. And it's an important part of science. Because there's a lot of things that happen, like did you know they measured something and they thought that they got something faster than the speed of light? But they actually had error, which they did not account for, which is that the satellites were not on the ground. They're in the sky. Yeah. Which, actually, it wasn't a screw-up, actually. They actually published it in a letter, which is asking why we got this result, because we don't understand what happened, what went wrong. So, they didn't do wrong, they did it right. It's just hard to account for everything, right? You need other perspectives. So pipettes deliver known volumes of liquid. We have transfer pipettes and measuring pipettes. So transfer pipettes are calibrated to deliver one fixed volume. The last drop does not drain out of the pipette. You should not blow it out. It delivers what it says, okay, with that stated uncertainty. They literally, depending on the grade of it, an A grade, they do this a certain amount of times. I forget how many, it's like 10 or something. where they have an actual person pipette, deliver, they weigh it out, see how much they got, correct it for density, and they do that over and over until they're within those stated error limits, okay? A measuring pipette is going to be calibrated like a burette. It's used to deliver a variable volume, and you've seen these before. We have a bunch of them in lab, such as like 5.6 milliliters. You'd have a starting delivery at 1 milliliter, and it terminates up at the 6.6 milliliters. Notice that you should always start at 1 and go up from there, because you don't want to start where it doesn't have any markings. It's very likely you're going to mess up, especially from air bubbles, okay? Because the air bubble is going to end up here. See that? So what you have to do is start at 1 and then let it go down to one of the markings. That makes sense? Okay. This is another example of essentially a micro pipette, but this one's a little bit more complex. This is actually a high precision one. It takes more machinery than handheld to get accuracy. Micropipettes are the bane of analytical chemistry. They're the thing the biologists use and think they're super accurate and have perfect accuracy and quote these numbers that are like 0.001 crazy accurate numbers, and they're like, this is perfect. And it just drives us analytical chemistry fucking nuts. Okay? If you actually look at the micropipettes in your book, first off, you will notice their accuracy is not very good. In relative uncertainty terms, their accuracy is far worse than transfer pipettes and burettes. Yep. Yeah. They're very convenient. They can be very convenient if they're well maintained and you know how to use them. But they trick people because they give you this, that's microliters, by the way. That happens all the time in this because the PowerPoints flip the damn symbols on me. If I actually put the micro symbol, it transfers to M. When it goes, this isn't Greek. Anyways, just you can figure it out, okay? Micropipettes, microliters, right? These tell you a number on the dial, right? And so it seems like that number should be accurate to what it says, right? And so people write that down and think it's accurate to what it says. But it is not. It typically has an accuracy somewhere around 10% to 20%. So its uncertainty is typically 10 to 20% of that number, meaning the last digit's worth nothing, right? It doesn't matter whether you set 955 or 951. Frankly speaking, that number probably is meaningless, that 1 versus 5 at the end, okay? Like that really, you're not measuring that at all. You're lucky if you get between 950 and 960, okay? That's doing pretty good. All right. The liquid is contained in this disposable polypropylene tip. Most of these are polypropylene. You can get other versions, by the way, for other uses. This is stable for most aqueous solutions and for quite a few organic solvents, actually, surprisingly. However, I highly recommend you do not use anything that is highly vaporous, that evaporates easily. And the reason for that being is the vapor will get up into the internals of this and will actually destroy the pipette after a fairly short period of time, okay? And so I've seen a lot of labs destroy these within 1 or 2 uses. And then these things are expensive. They're like $200 just to calibrate. So, chloroform will dissolve the tip and is easily gone into the vapor, which will then destroy the inside of this, and you won't have a pipette anymore pretty soon. It's not resistant to concentrated nitric or sulfuric acids, which I see people use all the time with these damn things. You can't believe how many freaking times I've seen that. You should never lay it on its side with solvent in it, okay? That's why it has this thing right here. You hook it on something, right? If it's steaming, vaporous, concentrated acids, don't leave it in there, okay? Don't leave it in there, period. It will destroy the internals. There's metal and there's plastics in the internal parts of these, okay, to make it work. Anything that will rust up metal easily will destroy the internals of this if you leave it. Do you guys know how to use these more or less? I'll actually talk to you guys in lab about actually using them. I find that most people have been taught in other classes don't really know. They kind of teach you guys a half-assed way instead of using them. Again, that nice digital reading on this micro pipette, don't be fooled by it. That number's bullshit. Do not be fooled, okay? Unless your pipette has been calibrated recently, your personal technique tested, micro pipettes typically have gross errors not represented on any of these tables, okay? Frankly, most micropipettes are meant to be calibrated every 3 or so years, typically every 2 to 5 years, okay? And you should calibrate them every 3 years. Large labs would do that. Smaller places just don't have the money to do it. Like I said, it's like $200 to get them calibrated, right? It's very expensive. In fact, you can get them calibrated, used micropipettes calibrated for you. You can buy them for $200, so it's kind of silly to get yours calibrated. We could calibrate them ourselves, though. That's actually possible. If you wanted, you could do a student lab doing it. The other part is, if you haven't tested your technique, what you'll find out very quickly is most people are absolute crap at this. Terrible. Like, they're doing really good if they're doing less than 30% error. Okay? Most people's technique is just awful. Like, really, really awful. These are the manufacturer tolerances for the micropipettes. You will notice very quickly that the percent errors on these are actually quite large. See that? That right there? That's 8%. Plus or minus 8%. Wow, right? You could have two measurements that are 16% difference between them. Wow, right? That's a lot more than you probably thought, isn't it? That's the manufacturer. That's if everything goes right. Volumetric glassware actually has amazingly great tolerance. See that? 0.02. I mean, 0.02 out of 1 is not great. It's 2%-ish. But when you get up to a liter, that's an amazing value. Percent-wise, it's fantastic. You're going to notice that volume measurements typically have percent errors that are way higher than weight. Weight is just far more accurate. Okay? Here's filtration. I don't think you really need much on that. There's a lot of different filtration methods, by the way. We haven't used even a fraction of them. Okay? Pay attention to this gravity filtration method. It really makes a huge difference following this through. Okay? If you don't do this, you're going to take hours to do a gravity filtration. If you do this, the gravity filtration is going to be done in like 20 to 30 minutes. Okay? Huge difference. It's because of the airflow. When you do a gravity filtration, you need air to exchange, and you need a pathway for the liquid to go through. Not that isn't blocked, right? Okay. Notice you do this right here, where you guide it along the side so it doesn't block down here. What happens every time that I see this is people try to do a gravity filtration. Gravity filtrations are much more accurate than doing vacuum filtrations. Okay? And what they do is they're in a hurry, so they just dump it in here. What they don't understand is that if you dump it in here, it's going to block it, right? And that means that what should have taken you 20 minutes is now going to take you 3 hours. So they cut out stuff that would have taken, 2 minutes to do, and they would have had to maybe spend 20 minutes on the whole thing. And they're cutting out these things to try to save a minute or two, and now they're wasting 2-3 hours. Always do the little stuff to get you set up for success, okay? Those cutting that out just hurts you. It doesn't help you at all. It's just gonna make your life fucking miserable. Do you guys have anything else you want to ask? Okay. Be careful with the drying, by the way. You gotta dry it to a constant mass, but the other thing is, if you start putting these in, make sure you don't have oil on them. Like typically these have grease on them. You put them under heat with grease, the grease runs, right? Which happens all the time, even to PhDs. Spreadsheets are fantastic. Learn to use your spreadsheets, okay? Absolutely amazing. But learn to read and organize spreadsheets. Don't just plug things in and go magic box, now it works, okay? Understand what you're doing. Okay. You all have a great day. We'll see you next time.